Okay, let's look at number 3 from this data analysis question. A student performs an experiment with a paper toy that rotates as it falls slowly through the air. After release, the paper toy quickly attains constant vertical speed as measured over a fixed distance. So this distance doesn't ever change. She always drops from the same height, and during this distance it travels at a constant speed. Look at this, distance and speed. You're already kind of thinking speed is distance over time. The aim was to find how the terminal speed of the paper toy varies with its weight. The weight of the paper toy was changed by using different numbers of paper sheets in construction. So maybe they add more paper on top, right? And as they do, it gets heavier and heavier. Remember that weight is just another term for gravitational force, which is measured in the units of gravitational force is newtons. Brackets here mean units of. Okay, let's move on. The graph shows a plot of terminal speed calculated from raw data and the number of paper sheets N used to construct the toy. The uncertainty in V, where's V? Here it is. This is number of sheets. The uncertainty in V for N equals 1, that's N equals 1, that's this one, is shown by the error bar. The fixed distance that the thing falls is 0.75 meters and has an absolute uncertainty of 0.01 meters. The percentage uncertainty in time to fall through the fixed distance is 5%. So that's for every value, right? 5%. Calculate the absolute uncertainty in terminal speed for N equals 6. Here's N equals 6, and N equals 6 is right here. You go over halfway, right, between, this is a very strange graph. The markings are very, very odd. And we're at 0.4. So this is 6, 0.4. Write that down as part of your answer. The speed is 0.40 meters per second, or meters seconds to the negative 1. We want to know the absolute uncertainty in this speed. We can't find it from the graph. It's not shown. It's not this. That's a different point, and it may be different uncertainty up here. In fact, it is. So you have to calculate it. How do you calculate it? Well, speed is distance over time. The percent uncertainty in V is a percent uncertainty in D plus the percent uncertainty in T. Can we calculate this way? That's the only other equation I can think of to find the percentage uncertainty. Can we find it this way? Well, we know this. It's 0.01 over 0.75 times 100%. We know this. It's 5%. So once we know this, the percentage uncertainty in V, we can use this equation to find the absolute. Right? We'll know this, we'll know that, 0.40, and we calculate delta V. So we go ahead, this is going to be 0.01, the absolute uncertainty, over the value of the measurement, times 100%, plus our 5%, plus 5%, and what do we get for percent uncertainty in V? .33%. Don't round yet. You put in that 6.33%. Delta V is the unknown. What's the speed at N equals 6? Oh yeah, the speed is 0.40. We wrote that down there. It's important to write down values that you obtain from the graph. It's usually one of the points that you earn. Just writing down the value from the graph is one of the points. Alright, times 100%. You find delta V, and it's plus or minus. Make sure it's just one sig fig. Let's see, 6.333 times 0.4 over 100. Whoa, can it be that small? I done this correctly? No. I multiplied by 0.1. So let's try this again. Times 0.4 over 100. 0.025. Plus or minus 0.025 meters per second. Same units as the measurement. Or with 1 sig fig, plus or minus 0.03. Draw an error bar corresponding to n equals 6. Aha, that means they want us to draw 0.03. 0.03, well, let's think about this. 0.03, from here to here is 0.05, and I want 0.03. So half of this is 0.025, which is which is exactly what I've got here. So I want to go half of this distance. Go halfway down, right about there, right? And then halfway up. There. Draw a line of best fit. Easy. Got it. Wait. Maybe I don't. Should it be curved? This is a really small uncertainty, right? If you do this, if you make this your line of best fit, do it the other way. This, if you make this your line of best fit, the line systematically underestimates the true value. The measured value, excuse me. The measured value. So this would be a bad line of best fit because every measurement is higher than the best fit line. If you try and do something like this, right, something like this, so that you have as many above as below, now you don't pass through this guy's data point, his error bars. So that doesn't work. So it has to be curved, right? It has to be kind of curved. And we might as well send it through the origin because it looks like we can. Okay. The student hypothesizes V is proportional to N. Use the data points, N equals 2 and N equals 4, to show that the hypothesis is incorrect. Proportional, directly proportional. So you're doing the ratio, the 2-point ratio test. Right? So let's get out our graph again. Find those 2 points. N equals 2, here it is. So the data, that's 2 comma, where are we? From here to here is, well, let's see, halfway between here and here is going to be, if you don't know how to find out, you just average them. 0.225. And then halfway from here to here is this value. So let's average 0.225 with 0.25 to get halfway. 12.6125. All right. And then that's n equals 2 and n equals 4. N equals 4. So it's obviously 4 is the x value. That's given. We come over. What's going on with this graph? Oh my gosh. Let's see. From here to here, what's halfway? Halfway is roughly this. From here to here. So that's 0.325. And then from here to here, halfway is this y value. So let's average those two to get the y value. 35 over 2. 0.3375. Did I do that right? Yes, I did. 0.3375. Did I do this one right? Halfway between 0.225. Yep, got that one too. Alright then. We're using the graph to see whether this is correct or incorrect. Well, no, we want to show that it's incorrect. So now, what are we doing? The ratio test, because it's a direct proportionality we're checking for. So you take the ratio of y quantity over x quantity. Right? For your first data point, let's do this one first, why not? You got 12.6125 over 2. Find what that is. And then V2, take the ratio again. V2 over N2. And now you're using the other data point they said to use, 4, comma, no, the y value, v, is second. 0.3375 over the value of n, which was 4, right? You calculate those, they're not going to be equal because they say it's incorrect. And you say, again, because the ratio of v to n isn't a constant, because of this, v and n, right, the things whose ratio is not a constant, v and n are not directly proportional. Or you could say just proportional to each other. Another student comes along and hypothesizes that there's a different relationship. V is proportional to square root of n. So without looking, the way that we test this is by putting v on the y-axis, radical n on the x-axis. Is that what we have? No! What have they done? They've squared the v and squared the radical n values to get v squared and n. Got it. Okay. So v squared certainly does equal a constant times n. Right? Explain how the graph verifies the hypothesis that v is proportional to n. And you say v squared, right, the graph of v squared against n makes a straight line passing through the origin. Therefore, v squared is equal to k times n. That's a relationship. And then you say square rooting both sides, write out square rooting, gives v is equal to the square root of a constant, which is just a constant, times the square root of n. So that's how you explain. Right, there it is. You have to square root both sides to prove the theory that the student proposed.